Hello, I am Pablo Escobedo from University of Glasgow, and today I'm here to present our work entitled Flexible Strain Sensor with NFC Tag for Food Packaging. My presentation is divided into 4 parts. I will start with a short introduction to show the motivation and backgrounds of the developed work. Then I will look at the materials and methodology in terms of the strain sensor and the wireless NFC interface. Next, I will go to the results and discussion section, where I will show the outcomes of the work in different aspects. Firstly, the sensor characterization, then the electromagnetic performance of the antenna, and finally the results of the strain sensing. After that, I will outline the conclusions of the conducted work without forgetting to acknowledge our funders and show the reference and contact information. As you are all aware, smart sensors serving as the interface between the digital and physical worlds are opening interesting avenues for remote monitoring of environment, agriculture, and healthcare applications. In particular, smart sensors can be applied to monitor the safety of goods, which is a key step particularly for food packages, as even slight damage could raise health and safety concerns. In that regard, the use of smart labels with physical sensors, such as strain and temperature, and also with wireless technologies such as radio frequency identification, RFID, or near field communication, NFC, can offer new possibilities for monitoring the packages and enable battery-less powering and data backscatter communication. Herein, we present a microchannel-based flexible strain sensor integrated with an NFC tag to detect, in a semi-quantitative way, the applied dynamic strain. The change of the sensor resistance at different bending or strain conditions will modulate the light intensity of an LED indicator. This system could be used then in food packaging for early detection of bacterial activity through strain sensors measuring the bulge or swelling of the package. Let's turn our attention now to the strain sensor description. The sensor consists of a flexible and transparent PDMS channel filled with conductive polymer PEDOT PSS. A detailed fabrication of the microchannel is available at one of our previous works, which you can find in the reference list. After the microchannel fabrication, conductive polymer PEDOT PSS was injected into the microchannel. Then, the electrodes were dried and fixed using metal wires. In the figure, you can see the optical image of the developed strain sensing system, including the NFC tag, the reader, and the sensing module. This leads me to my next point, which is the NFC interface. The designed tag antenna consists of a printed circuit board, planar coil matched to the internal capacitor of the NFC transponder chip, which is in this case is from Texas Instruments. The tag was designed to resonate at 13.56 MHz, which is the frequency compatible with NFC applications. Therefore, it can be operated with any NFC-enabled smartphone. Considering the input capacitance of the RFID chip at this frequency, 13.56 MHz, which is around 35 picofarads, the required inductance value was approximately 3.9 microhenries according to the resonance frequency of a parallel LC tank circuit. However, to reduce the antenna dimensions, a 1.85 microhenries inductor was designed, and then an external capacitor of 39 picofarads was placed in parallel to the internal capacitor to achieve resonance at the desired frequency. So let's now move to the next section, results and discussion. Firstly, we need to highlight that the developed strain sensor is resistive, which means that its resistance increases with increase in the strain value. This is illustrated by this figure, which shows the temporal normalized resistance response of the strain sensor when it's bent to different angles. Based on this, and in the presence of an NFC reader, the LED in series with the sensor will glow with different intensities depending on the applied bending or strain. Regarding the electromagnetic performance of the antenna, the left figure in this slide shows the experimental measurements of the inductance and quality factor of the PCB coil before attaching the chip. It can be seen that the inductance value at the frequency of interest, which is 13.56 MHz, is very close to the design value. Once the chip and the external capacitor were attached to the PCB, the resonance circuit was completed. Thus, a new frequency characterization was conducted by measuring the impedance and phase of this parallel resonance circuit. As can be observed in the figure on the right, the resonant frequency is very close to the desired working frequency. As previously said, the brightness of the LED will depend on the applied bending or strain. To prove this, the light intensity values were measured using a lux meter mobile application. This figure shows the decrease in the intensity of the brightness with the increase of bending angle. In particular, the brightness was highest, around 67 lux, for the relaxed or no strain condition, while the LED was found to be almost off, with around 8 lux for the maximum strain condition. Then, as a proof of concept, an example of application of the developed system attached to a food package for mid-spoilage detection is here shown. Under normal conditions, that is, when the product is suitable for consumption, the LED will be on with the maximum brightness level when a reader approaches the tag. The growth of bacteria in the food package will lead to gases and hence the swelling of the package. In such a scenario, the inflated package will increase the resistance of the strain sensor, and then the LED will be off, meaning that the food is unfit for consumption. So, in conclusion, let me sum up the main points. This work presents a flexible strain sensor integrated with an NFC tag to detect the strain in a semi-quantitative way. The sensor was fabricated using a flexible polymer PDMS microchannel and conductive polymer PEDOT PSS injected into the channel as the active material. The sensor showed a maximum of 3-ordered increase in resistance for around 100 degrees bending. The resistive strain sensor was then connected to a custom-developed NFC tag system containing an LED indicator, whose light intensity was modulated as per the strain level. Finally, as a future scope of this work, a flexible version of the NFC tag system will be developed to achieve a better integration with the package and demonstrate its applicability to food spoilage detection in intelligent or smart food packaging applications. Before ending these presentations, we would like to acknowledge the NewCam project, which supported this work. And also here you can find the contact information and the full reference list of works cited during this presentation. That brings me to the end of my presentation. Thank you very much for your attention.